Okay. Uh, in this chapter, chapter number 15, we are doing the secret codes. And we have started that we are talking about the process of converting a message into a string of numbers or letters according to some rule that only the sender and the recipient know is called the encoding, and the process by which the recipient converts the received string back to the original message is called decoding. We have given some example, and then we have discussed what are the so at current time we use the encoding and decoding method and for the codes, and those codes are known as RSA codes. And why these codes are so like intelligent and like very hard to decode by some third party or like some other person, because um, we set a criteria that even a computer cannot break. So what is that criteria? That computers find factorization of large numbers very difficult. So that is, by this we mean that we take two primes, each of 200 digits, we multiply them, and then we keep those primes to ourselves, and then we give the product of those primes to computer and try to ask the computer to find out the factorization, and that's very hard to do that for even for a computer. So that's why these RSA codes are uh, very strong and difficult to break. So we then explained how these RSA codes work, like how encoding works and then how decoding works. Now we are going to talk about the security of these codes, like how strong they are. Okay. So the question is, how strong, how secure is RSA code described above? Described above. In other words, if an encoded message is intercepted by a third party who knows the public available values of N and E, how easy it is for them to decode the message. So let's say, in other words, if an encoded message is intercepted by a third party who knows the publicly available values of n, which is the product of two primes and some exponential number e, how easy it is for them to decode the message. Okay. Well, at present, the only known way to decode is first to find the value of p minus 1 into q minus 1. So it present the only known way to decode is first to find the value p minus 1 into q minus 1, and then to calculate d, and then to calculate d and use the decoding method. Okay, so to explain what is D and the decoding method, let me just remind you something. So let's say we have an encoded message and we receive the list of numbers which are known as n1 to nk, and we need to find out the original numbers m1 to mk. So this is the process. We have a message in the text, we convert them into the numbers, and those numbers are m1 to mk, and then we encode them to numbers which is n1 to nk. Okay, now what we do, we try to solve this congruence equation with the following values, and then but mi is just a solution of the congruence equation, this one. Okay, so what we do, then we use the proposition 14.1, sorry, 14.3, and we have to solve such congruence equation. So since E has the form chosen to be co-prime to the product P minus 1 into Q minus 1, we use the Euclidean algorithm to find a positive integer D such that DE is nothing but 1 mod this product. And then the solution to this congruence equation is going to be this one, which is similarly x congruent to ni power d mod n. Now, this solution must be original number mi. So you can do that for each ni, you can always find mi. Okay, so this is the way. So this is the d and the product we are talking about here in the security section. Okay, calculate d and use the method above, working out dth power modulo n. Modulo n. N is the product of P and Q. Okay. However, P minus 1 into Q minus 1 is nothing but P into Q minus P minus Q plus 1. And that is N minus P plus Q plus 1. So if we know N and can find P minus 1 into Q minus 1, then we can also find P plus Q. Okay. But then we can also find P and Q. also find P and Q, but we are supposed to hide them. So since they are the roots of the quadratic equation, since they are the roots of the quadratic equation, that equation is x square minus p plus q x plus n is 0. In other words, in order to be able to decode a message, in order to be able to decode a message, third party needs to be able to find the prime factors. A third party needs to be able to find the prime factors P and Q of n. But as we have explained before, starting the description of RSA codes, if P and Q are, but if P and Q are very large primes, both with about 200 digits, then no computer on earth will be able to find P and Q. Given only their product. Only their product, which involve the public key. So in other words, the code is secure. The code is secure. Okay. Even if increases in computer power enable us to factorize product of 200 digits prime in the future, it will be a simple matter to retain security just by increasing the number of digits in our primes. What is not clear is whether someone in the future will discover a clever new method of computer factorization of large numbers that makes all these codes insecure. Let's see. Let's leave that on future. Okay, let's discuss a little bit of the history also. A history of these primes. A little history. So, remarkable idea that it might be possible to design a code where knowledge of the encoding process does not mean that only one can decode messages, was proposed by Diffie and Hellman in 1976. So the idea of encoding, the idea of designing a code like RSA code is given by Diffie and Hellman in 1976. And a year later, Rivest, Shamir, and Adelman found such codes. Such codes, namely the ones described above, which are known as RSA codes in honor of their discoveries. Okay. A few years ago, however, a few years ago, however, some new facts came to light. In Cheltenham in the UK, and it turned out these codes had been discovered several years earlier by Elias Cox and Williamson. These discoveries could not be published at the time because of the classified secret nature of the work at GCHQ. So, for an interesting account of this and many other aspects of secret codes through the ages, read the book by Simon Singh, listed in the further reading at the end of this book. Perfect. So we will end this one, and then we'll do this history section here, and then we will try to do few exercises. So let's say we have an exercise 1 to say that find the primes. Maybe I'll do the exercise in the next part.